Hello, my name is Robert Smith, and I'm with New River Community College as academic assistants, and today we are looking at calorimetry. We're given the problem states 664 grams of water is heated from 5.8 degrees Celsius to 46.7 degrees Celsius. Calculate the kilojoules of heat absorbed by the water. So we know in this particular case that we're dealing with calorimetry, in which case we need to look at the heat that is being absorbed. And to do that, we're going to use the equation Q for heat is equal to ms delta T, mass times the specific heat times the change in temperature. And we can leave this, in this particular case, and for this particular equation, we want to leave our temperature in Celsius. Normally we convert to Kelvin, but the relation in this particular formula due to specific heat is going to be in Celsius. So we're going to leave this in Celsius. And then it's just a matter of plugging everything in. So for our mass, we have 664 grams. For our specific heat, we're looking for the specific heat of water. And that's something that you can look up in your book, and you should probably memorize over a period of time, but it's 4.184 joules per gram degrees C. And then our delta T is simply going to be our T final minus T initial, which is 46.70 degrees C minus 5.80 degrees C. So coming back to our equation, we can simply plug these in. So 664 grams times 4.184 joules per gram degrees C times our delta T is going to give us a value in joules. So we're going to want to go ahead and change those. 46.70 degrees C minus 5.80 degrees C. And then that's going to give us a value that's going to have it in joules, and we're going to want kilojoules, which is what the problem asks for. So let's go ahead and do the conversion rate right now. 1 kilojoule for every 1,000 joules. When you do the arithmetic out, the answer comes to be 114 kilojoules, keeping to 3 significant figures. The next problem states 3.541 grams of naphthalene was burned in a constant volume bomb calorimeter. The temperature of the water increased from 20.82 degrees Celsius to 29.55 degrees Celsius. The heat capacity of the bomb plus the water was 11.70 kilojoules per degree Celsius. Calculate the molar heat of combustion for the naphthalene. In doing this, you're going to want to start by identifying the formula. So in this particular case, we're dealing specifically with a bomb calorimeter, in which case you're going to want to use the formula Qcal is equal to Ccal times delta T, change in temperature. And our Ccal is given right here. And our delta T is the difference between these two values. So rewriting this, you can see 11.70 kilojoules per degrees C times 29.55 degrees Celsius minus 20.82 degrees Celsius will get us our heat of the calorimeter, which after doing the arithmetic you'll find is 102.1 kilojoules, keeping to 4 significant figures. But recall that what we're looking for is the molar heat of the combustion of the naphthalene. So, looking at this, we have to look at the heat of the system. Well, the heat of the system, because of this particular instance, is going to be 0. So Q sys is equal to 0. Therefore, we can make the presumption that the heat of the calorimeter plus the heat of the reaction is going to equal to 0. Well, if the heat of the calorimeter is 102.1 kilojoules plus the heat of reaction, simply subtracting 102.1 kilojoules to both sides, you'll find that the heat of reaction is equal to negative 102.1 kilojoules. And recall that the negative simply means that it is releasing the heat rather than drawing the heat in. So the next thing we're going to want to look at is how many grams of naphthalene we have, which is given in our problem, 3.541 grams. So we're trying to find the molar heat, which is the heat that relates to mole. We want our end result to be kilojoules per mole. So our molar heat is going to equal the heat of reaction, 102.1 kilojoules, divided by 3.541 grams, which is what we're given. So for every 3.541 grams, you have a release of heat of 102.1 kilojoules. And then we're going to simply want to multiply that by the molar mass of naphthalene, which is, after you do the calculation out by adding 10 molar mass carbons and 8 molar mass hydrogens, 128.2 grams for every 1 mole. Grams and grams will cancel each other out, and you'll be left with kilojoules per mole, which, when you do the calculation out, you'll find that it's negative 3,696 kilojoules per mole. Let's look at another problem. A piece of metal alloy with a mass of 24.676 grams at 98.89 degrees Celsius was placed in a constant pressure calorimeter of containing 100 milliliters of water. The water temperature rose from 25.2 degrees Celsius to 27.31 degrees Celsius. What is the metal alloy's specific heat? Going back to our specific heat formula, which, if you recall, is Q is equal to MS delta T. Involved that just a little while ago. We'll come back to that formula in just a moment. But the first thing you're going to want to realize is that the heat of the metal is going to equal the negative heat of the water in the calorimeter. So our heat of the metal is going to be the opposite of the heat of water. So, coming back over here, we're going to do the heat of water, because we can calculate that from the temperature difference, is equal to the mass, which is, if you look at 100 milliliters of water, every milliliter is a gram, so 100 milliliters is 100 grams. So 100.0 grams times the specific heat of water, because we know that, 4.184 joules per gram C, times the change in temperature, which goes from 25.2 to 27.31. So 27.31 minus 25.20. Zooming this out, you'll find that the heat of the water is 882.8 joules. Recall that the heat of the metal is going to be the opposite of the water. And the reason we did the water is because we know what water's specific heat is. We know what the mass of the water is. We do not know enough about the metal to make a determination of specifically the specific heat, nor do we know the change in temperature for the metal. So, Q metal is going to equal negative 882.8 joules, which means it's simply giving off that amount of energy. So, in calculating the specific heat, we can find negative 882.8 joules is equal to the mass, going back to our original formula. So mass is 24.76. Took it up here. And we know our change in heat is going to go from 98.89 down to 27.31. So 24.76 grams times S, some unknown specific heat, times the changing temperature, which is 98.89 degrees C, minus 27.31 degrees C. You can do the calculation out. You could switch the algebra and make it so that you're solving for S specifically. Simply divide this whole thing by, you want to do the stuff inside the parentheses first, and then multiply it with the 24.76, and then take that whole value and divide it from the 882.8 joules to get your specific heat. And when you do that, you'll find that S is equal to negative 0.498 joules per gram degree C. One more problem. This one states 100 milliliters of 0.5 molar hydrochloric acid is mixed with 100 milliliters of 0.5 molar potassium hydroxide in a constant pressure calorimeter. The initial temperatures of the hydrochloric acid and the potassium hydroxide are both 25.2 degrees Celsius. and the final temperature was 28.65 degrees Celsius. Assuming that the densities in the specific heats are the same as the water, which is 1 gram per milliliter and 4.184 joules per gram degrees C, calculate the molar heat change of neutralization. So that's a lot. Well, the first thing we're going to want to do is calculate the mass. We're given 100 milliliters of our acid and 100 milliliters of our base. So, which I underlined in opposite order for whatever reason. So recall that for every 1 gram, every 1 milliliter is equal to 1 gram, given by our conversion right here, our relation right there. So we can easily say that there's 100 grams of acid and 100 grams of base, which means our total mass is 200 grams. That's the first thing I want to do. Then we're going to want to look at our heat of solution. We're going to call it the heat of solution. And that's going to equal our mass times our specific heat times the change in temperature. Well, our mass is given as 200 grams. Our specific heat was given to us as the same as water. And our change in temperature is simply going to be this 28.65 minus 25.20. So grams times 4 joules per gram degree C times 28.65 degrees C minus 25.20 degrees C. When you do the arithmetic out, you will find that our heated solution is 2.89 kilojoules. I'm going to skip the step of kilojoules, but you can go ahead and do this because this whole equation is going to result in joules. So you're going to want to do the conversion of 1 kilojoule per 1,000 joules. Then I did that specifically because our end result has to be in kilojoules per mole. That's how molar heat is calculated, or represented rather. Then you're going to have to recognize that the heat of the reaction is going to equal the negative heat of solution, which is going to make it negative 2.89 kilojoules. The last step involves converting your molarity to moles so that we can then take that and convert it to molar heat. So thankfully the molarity for both of these is 0.5 molar, which makes it a lot easier because then you don't have to find the difference of the two. So in converting it to moles, recall that molarity is equal to moles per liter. And therefore, moles are equal to molarity times volume in liters. So we're going to just put a V there. So that equals 0.500 molar, or moles per liter, times the ultimate liters, which we have given to us in the form of 100 milliliters and 100 milliliters, which in this case we're looking at. But we're just going to stick with the 100. So 0.100 liters. That's just converting it. Liters and liters cancel each other out. And you're left with the moles, which are 0.0500 moles. So the heat of neutralization is going to equal negative 2.89 kilojoules divided by 0.500 moles, which is equal to negative 57.8 kilojoules per mole.